Hey everybody, thanks for tuning in. I'm going to do a brief video here just introducing some of the concepts that first appear in Chapter 2, and then we're going to use them the whole semester. So I'm just going to get right into it. The first thing that you want to be familiar with is this idea of a normal curve. And so this shape, when you see or hear that data is normal, or you have a normal distribution, also known as the bell curve because it looks like a bell. You're going to have data that is symmetric, meaning that it's, the left side is similar to the right. I can make this a little nicer, I suppose, with the biggest part being in the middle. And there's some other features. One is that the middle, right smack dab in the middle of the graph, is where you're going to have the mean of the data set. And we say that X bar is the sample mean. And sometimes if you're working with a population, which is less of the time, but mu is the Greek symbol that represents the mean of a population. So if you calculate the mean, or you are given the mean, that's the value that would be in the middle. And then the numbers that kind of are going to come off this, if you're going to be labeling things, is where the standard deviation piece is going to come in. And standard deviation is a little trickier, but in general you can think about the standard deviation as a measure of spread. And so if you use some technology or you're given standard deviation and it just gives you a number, let's say that your sample standard deviation, we use the letter S to represent that. Let's say your sample standard deviation is 2 versus some other data set where it's 5. Those numbers right now don't have a lot of meaning to us, but for sure we can say that this data set is more spread out. If you have a clump of data that, let's say the average is 5, and then you have kind of the whole data set, between 2 and 7, versus a mean of 5, and this goes all the way from 1 to 10. This one over here is going to have a larger standard deviation. It's more spread out. So a lot of times, if you want kind of a general picture, you can say that this first position is going to be your X bar plus S. And then the second hash mark would be X bar plus 2S and X bar plus 3S. As I'm drawing this, it looks really sloppy. Let me do a real quick kind of concrete example. If I give you make up some data and I say the mean is 21 and the sample standard deviation is 3, you're always going to put the average, the mean, right in the middle. And then one standard deviation from the mean would bump this up to 24. 2 standard deviations from the mean would bump this up to, you guessed it, 27. 3 standard deviations from the mean would bump this up to 30. But standard deviations are going to go in both directions. If you went down 3, how did I get this number? I did 21 minus 3. How did I get this number? I did 21 plus 3 standard deviations. So you can start seeing kind of a pattern, if you're looking at it kind of up by 3s, down by 3s. But you're grouping the data into chunks. And these chunks are how many standard deviations you are from the middle. If you're above average height, your data might fall over here. If you're below average height, maybe your data falls over here. But let's just say your height was 15. I could also describe that height as 2 standard deviations below the mean. If you are the tallest person in the class, maybe you're off the charts, I could say that you're 1, 2, 3 over 3 standard deviations from the mean. Generally, we look at the 3 deviations on the left and the right because most data sets, almost all of the data is within 3 standard deviations. So that's kind of the basic of how a standard deviation is structured. Now, I want to be a little more specific with this thing called the empirical rule. A nice little graphic here. So empirical rule is sometimes called the 68, 95, 99.7 rule, if you like numbers. And it is a great kind of resource when you are working with the normal curve. Or the prompt says that the data is normally distributed. It means that the data is playing by a certain kind of set of characteristics, and one of those meaning that the empirical rule could apply. Similar in traditional mathematics, if you're working with a quadratic, something that has a power of 2. Because it's a quadratic, you can use the quadratic formula. It's going to be a parabola. Maybe you could factor it. So similarly, if you're working with normal data, the empirical rule will be able to be applied. All right, so what does it mean? Remember that right smack dab in the middle is x bar. And each one of these kind of hash marks represents a standard deviation. So this position right here, you could say is 1 standard deviation above the mean. But there are now some percentages attached to it. And so if you look at the top, I think the top is the easiest to first explain. What this means is that if this is the true middle, the mean, then 50% of the data is going to be above the mean, and 50% of the data is going to be below the mean. If I calculated data on anything, and you find the mean, that means that half of the values are going to be below it and half are above it. That's the way averages work. But now if you want to tie some percentages to it, which can be handy in making conclusions, making predictions, making conclusions, what this says is that 68% of the data will be within 1 standard deviation. And that's what's tried to show here in orange. So if I go back to my last example, in this instance, I could say that 68% of the data is between 18 and 24, tying it to an actual number. But every time you get a little further out, more data is going to be included. So the next kind of chunk, let me change colors. We'll do a yellow. This next chunk is 95% of the data will be within 2 standard deviations. The further I go out, the more people are included. I mean, just think about this with your heights or your weights or your commute time or your number of siblings. If I say that the average is, some number, and then I just start expanding and making a range of values around that, no matter what you answer, eventually you'll be included in that. And so the third standard deviation, 99.7. So all but 0.3% is going to be within 3 standard deviations. Now, if you wonder how these numbers, I'm circling them right now, are calculated. The idea, for instance, if I wanted to show you how 13.5 is calculated, the idea is if you do 95%, subtract the 68%, that's orange, 78, 88, what'd that be? I don't know, 78, 88, that's 20, like 27. And then cut that in half because it's symmetric. That's where you're going to get the 13.5. So the symmetry is helping us out a lot with this too. So how is this going to be worded in a question? So a lot of times in stats, you want to make conclusions that involve percentages. And so if you had this, only this information about a data set, but then it said, hey, what's the probability that, let me erase some of this. What's the probability that a data value is above 24? Data is greater than 24. So this is where a little math comes in, and if I shade it, because I like these colors, here's 24, and it's saying, what's the chances that your data is up here? Well, here's what I know with absolute certainty. This shaded piece in black is 50% because it's half. And then if I jump to my little cheat sheet here, this chunk between the middle and the first standard deviation is 34%. Sorry, I'm going the wrong way. So that cumulative area then is going to be 84%, 50 plus 34. But if the whole thing is 100%, then this has to be 16%, meaning the green space. So I could say as a conclusion that the chances of a data being bigger than 24 would be 16%. Similarly, less than 24, meaning all this black area, if X was less than 24, I would say it's 84%, just by breaking things up into chunks. And so we're going to be able to use the empirical rule, along with what we know about the mean and standard deviations, to make a lot of quick conclusions about percentages attached to data values. All right, more to come on this, but this is going to be a big part of the class. So thank you for tuning in. I appreciate it.